I'm Juan.
And I'm Alex. We're here at NOAA. And we're here to talk the atmosphere with Brian Neely. Let's go.
Hey guys, how's it going? Ready to learn about lasers?
Oh yeah.
Awesome, let's go. A LiDAR sounds like a pretty fancy instrument, but it's actually very similar to just having a laser pointer. Look at the laser pointer and it's going through the room. You can see light scattering off on all sorts of directions. You can see the beam. And that's all we're really doing is we're recording the impacts of that light that's scattering back from a laser pointer. Our laser pointer just happens to be really big, and we have a big telescope to see very far away. I study several components of the atmosphere. I study the part that we're in right now called the troposphere. And in that part of the atmosphere runs from the surface all the way up to 10 or 15 kilometers where the tropopause is. And in that part we have weather and we have clouds and there's lots of dust. And I also study stratospheric aerosols. And the stratosphere is the part right above the troposphere. And it's the part where the ozone layer is, and it's affected by volcanoes and all sorts of emissions, but it's slower to change. There's no weather like you would normally think of here in the troposphere up there. And I studied changes in that part of the atmosphere over long periods of time. This is a pretty typical aerosol LiDAR. LiDAR stands for light detection and ranging. So you have to have something that makes the light, and what we use is a pulsed laser. This is the laser right here, and this is really the heart of a LiDAR. You have to have the light source. And besides that, to control the light source, we have to have something that keeps time. Like I explained earlier, when we shoot a pulse of light out of the laser, we have to record what time we did that, and then we wait for the light to come back and we record what time we detect it. The other main components of a LiDAR are the detection, and to collect the light that we send up with the laser, there's a big telescope on the other side of this whole electronics array. And you can see here, this is our telescope. It's a 30 centimeter mirror, and it captures the light that comes back from the dome onto this little dot here, which is a liquid fiber, and that fiber takes all the light that we collected and brings it over to here to these are the actual detector. So I've kind of described the light part and the detection part, but for all that to work together we have to have a computer that controls all the different systems. We have a computer here, and you can see this is our data acquisition screen. So this is actually the program that collects the data, and you can see a pretty typical data profile here, and you can see it makes the shape of the atmosphere. And I have to do some pretty heavy analysis and math to take this data and turn it into a profile that tells us how many aerosols are in the air. Well, I'm a graduate student here. I'm finishing my PhD, and I came into working at NOAA, and there were instruments already here, and I got to learn about them and use them, like the one on top of the roof. From what I learned, and I took classes about it, I was able to apply my new knowledge to build an instrument. So I have designed one instrument, and we've also been working to improve them and automate them. So I've been designing systems that allow us to take more and better data and kind of taking the human factor out of data collection. My instruments are located all over the world. I have one here in Boulder, just right near us now. We have that one here because we have this wonderful lab, and I'm here to operate the LiDAR, and we're studying the stratosphere, and that's not really affected by the troposphere, so it doesn't impacted by regional pollutions and emissions and anthropogenic sources. But we also have them located in American Samoa, Hawaii, on the top of a volcano called Mauna Loa, and then we also have one in Greenland. And we have those in those places because we're trying to measure the background atmosphere. We don't want to be measuring, effects from cars and people. We want to try to look at the long-term changes, not just local variability. And so we put them in these places that are away from people, and they're up in the clean atmosphere. It's trying to look at the larger scale trends. You can actually run the LiDAR. And I'm opening the dome here. You can see it opening now. And I can do this wherever I am in the world. If I can run the LiDAR in Greenland, I can run the one here, I can run the one in American Samoa, all from my phone, and they also run themselves. And that really allows us to collect more and better data. So our instruments are quite large. LiDARs are about the size of 2 refrigerators put together, so they're very hard to move. But here in Boulder, we build the LiDARs and then we take them to, we break them down and take them to Greenland and Hawaii and Samoa because we have the facilities here to calibrate. So in that vein, I write papers and I try to document everything I do, and that doesn't really have a direct effect on the local community. But also when we have fires, such as the canyon fires we had last summer, the ones earlier this year, I can detect those fires and measure local air quality, and we try to make reports and let people be aware of that as well. So I have this kind of global perspective where we're trying to understand climate and have that knowledge disseminated to the broader public, and then on a local scale, I look at air quality problems.
Well, it was great meeting you, Ryan.
It was wonderful. Thanks for coming by, guys. Nice to meet you.
Thank you so much, Ryan.
I hope you guys learned something today. And have a safe trip home, okay?
We will.
Bye, guys.
Thank you, Ryan.